Hello everyone, in this video I'm going to be going over enthalpy / standard enthalpies of formation. So these two in the chapter are separated by quite a bit. They're not right next to each other, but I feel like personally they should be next to each other, so I'm going to throw these two together in one video, and then I'll do a separate video on Hess's law because that one can be pretty difficult, so I should be posting that one hopefully by the end of this weekend if I end up getting to it. Again, a very busy person, so I will definitely try to make a video, but there are no promises, and I do apologize if I don't get to making all the videos for the exam, but yet again, busy person. So for this video, again, I'm talking about enthalpy and standard enthalpies of formation. I'm going to be talking about general notes, and then I'm going to go into two already done out problems just to show you two different processes of kind of things that we'll see with enthalpy, and then one practice problem for us to do together. I'm not going to do any extra practice problems for us to do together. Usually I shoot for two, but these ones can be kind of long, so I want to keep the video short and concise. And same thing as always, if you still have any questions, definitely talk to Professor Sherlock. Office hours, he's great. One-on-one, he's a very, 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 very nice person. As long as you're showing interest and being respectful, he's very, very nice to talk to and very respectful. Okay. And then again, you can always reach out to me if you have any questions. Okay, so let's get started talking about what the heck enthalpy is. So I'm just going to change my color here. Enthalpy is the heat needed to carry out a reaction. So we can look at it as being plus delta H or minus delta H. So enthalpy is denoted as delta H, but when it is positive delta H, it is endothermic. So I always like to think of the scenario where you have isopropyl alcohol on your hand. What isopropyl alcohol does on your hand, you might notice that it gets kind of cold and then it evaporates really quickly. So isopropyl alcohol is actually having an endothermic reaction on your hand. So it's taking the heat from your hand and using that to evaporate off, right? So that's why your hand feels cold, because it's removing heat from your hand in order to do that reaction, right? I'm trying to think of an exothermic one that I can think of. There's not one for exothermic that I can think of off the top of my head, but if you have an aqueous solution and you're adding some kind of a compound into it and the test tube gets really hot, that means that it's an exothermic reaction. So the delta H is negative. That means that the reaction is removing heat, and that's why it feels hot, because it itself is removing heat, right? So as I have written down here, so exothermic or endothermic takes heat from the surroundings, which makes the surroundings colder, but makes the reaction gain heat, so it can do its reaction, but it itself doesn't usually feel hot. It's just cold from removing it from the surroundings. And then exothermic releases heat to the surroundings, so that's why the test tube would get hot if it is exothermic. Endothermic, a test tube would be cold, right? Because it's removing the heat and adding the heat is exothermic. So let's take a look at enthalpy of formation and the different equations and different notes to have for that, right? So the standard enthalpy of formation is that the enthalpy of the reaction, so the total enthalpy of the reaction, is equal to the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants, right? So I'm going to say this again throughout all these videos. I'll probably keep that as a reminder, because I know some of you guys might be watching these and be like, how am I going to remember these equations, or how am I going to have enough room to write these down? Professor Sherlock's going to be giving us a whole equation sheet, so we don't have to write them down. So don't worry about that. But that is the equation that we're going to be using for this standard enthalpies of formation. So these H values will be given to you, right? The only one that you're going to have to find is the delta H of the reaction. It's possible that he might give us one where he gives us the delta H of the reaction and we have to find the sum of the products or something. But again, simple algebraic manipulation there. As long as you have one of these values, you can solve for the other ones, right? But all those H values that you need will be given to you. And if they're not given to you like in the problem, you're going to find them on a table like this, right? So here's the heat standard enthalpy here, and all those values are there for each corresponding compound. Right. So I just want to add a little bit of a note here. The delta H of an element or a diatomic molecule or gas will always be 0, right? So if you have something like silver as a solid, that's going to be 0. If you have H2, which is a diatomic molecule, that's going to be 0. And then just as a reminder, this is something that some teachers might have gone over in high school chemistry, but I'll do like a brief little overview. Diatomic molecules or gases are called the Enthalpies, right? So when they are in the air and unreactive, and what the most common form that you're going to find them in, it's going to be diatomic, right? Which means that there's 2 of the same atom. So we have oxygen as an example. We commonly see that a lot. Chlorine is an example that we commonly see, and H2 is an example that we commonly see, right? So these all have a charge of 0 when they are, up floating around in our atmosphere, and they also have a heat of formation of 0, right? So again, the Enthalpies. So we have H2, O2, N2, Cl2, Br2, I2, and F2. So those are just ones to kind of watch out for if you're, doing a problem and you see them and you're like, oh my god, I can't find the heat of formation of them. You can assume it's 0, right? So let me see if I can find some examples of those. Yeah, Br2, which is a Enthalpy. It's the Br there. Let's see if we can find another one that's 0. Cl2, Enthalpy. Yeah, and then here's another good example, right? So F as a gas by itself, you might think, oh, that's an element. Cool. That's going to be 0. It's not 0. It's actually 80. That's because it's not in the diatomic form that it needs to be in order to be stable. So the F2 one is 0, but the F1 isn't 0. It's 80, right? So just kind of keep that in mind as you're going through these. Okay, so I'm going to show you a problem that I had done out already of the... let's see if I can find it. I think it's this one, I believe. No, okay, so it is this one. Okay, so practice says, given that H2 gas plus Br2 liquid yields 2 HBr gas, and the delta H for this reaction is negative 72 kilojoules per mole, calculate the amount of heat released when 1 kilogram of Br2, this is a lot of words, Br2 liquid is consumed in this reaction, right? So let's break this down, right? So we have a reaction happening, we're given the heat, and we just want to find out how much heat is released when 1 kilogram of this is consumed, right? So we're told, okay, here's the standard equation, and here's how much heat is released per mole. So we have to find out how many moles are occurring in this reaction, and then we can find out from there how much heat, because heat is given to us in kilojoules per mole. So we can find out how many moles there are, we can find out how many kilojoules are released, right? So what I did here is that I first found the moles present in 1 kilogram of Br2. So I did 1 kilogram of Br2 times 1,000 grams in order to get it into grams. And then I divided that by the molar mass, and from there I got the moles, right? So I get 6.26 moles of Br2. And then from there, all I did is I did the molarity times the delta H that we were given in order to cancel out the moles and get the heat. I got 450 kilojoules released, right? So you might be looking at this and you're like, why is it not negative? It was negative here. That's not how math works, Grace. I understand that's not how math works, but because we're saying that it is released, we can just not put the negative there because that's telling us that it's going to be negative, right? So if you remember that the delta H, if it's negative, that means that it's being released and it's exothermic. But if you were to just ask, like, what is the heat released, you would say 45 or 450 kilojoules. But if we say 450 kilojoules released, we can just keep it positive because the release is telling us that it would be negative. Okay, now on to another kind of like practice, aka how to calculate, and this is dealing with the standard formation, standard enthalpy of formation. So again, the equation is the delta H of the reaction, so the enthalpy of the reaction is equal to the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. So how I like to think of this is that the delta H of the reaction is equal to the moles of a product plus the moles of the other product minus the moles of a reaction, so like times the H of the reaction for all of these, or the reactant, plus the mole times the H of the reactant, right? This probably looks like gibberish to you, and you're probably like, what? What? This is like too many words going on. But that's how I kind of think of it. You can think of it just as this, and just to remind yourself, if there's more than one mole, then to multiply it by the amount of moles. But I'll show you an example of what I mean by that, right? So here's the example. So we have H2 as a gas plus F2 as a gas is going to yield 2HF as a gas. So when we go to the standard enthalpy table, I already went and did it for us. We find that H2 as a gas is diatomic. We can know that it's 0, but if you look at it on the table, it will tell you it's 0 as well. Plus the F2 of the gas is also 0 because it's diatomic, and then it will yield H2HF, which HF alone, not two of them, just HF by itself, 1 mole of it, has a delta H of negative 271.3 kilojoules per mole. So in order to find the delta H of the reaction, what I did is that I did 1 mole of H2 times 0, which is the H of the product, plus the other product, which we have 1 mole of it, times 0, which is the enthalpy, minus the reactant, which we only have 1 reactant here, and there's 2 moles of it, so we did 2 times the enthalpy that we found in the standard enthalpy of formation table, right? And once we do that out, we get that the delta H of the reaction is negative 543.2 kilojoules per mole, right? So that's just an example of what something would look like and how I kind of think of it. I do have one practice problem for you all to try. We'll kind of work through this together. If you feel confident in it, again, try it out yourself. Make sure that you have the standard enthalpy of formation sheet with you as you do these. Okay, so I'm going to go through them, right? So calculate the standard enthalpy for this reaction here, which is 4HBr gas plus O2 gas yields 2H2O plus 2Br of a liquid. And I'm keeping that in mind that this is the equation. So the first thing that I like to do is I like to find the standard enthalpy of formation for each of these, right? So let's look at HBr first. See if we can find it in this chaotic mess of a table. So what was it? It was HBr. Maybe it's in Br. Let's see. B. HBr, let's go. And it's as a gas? Oh my god. Easy find. Okay. It's negative 36.2. So negative 36.2 kilojoules per mole. I'm going to assume it's in kilojoules per mole. Let's go. All right. I'm getting way too hyped about this. And then O2, I'm pretty sure it's diatomic, so it should be 0, but let's find it just to check. It's always good to check, you know. O2, let's go, 0. Guys, I'm like just hyped to be done this video right now. I've been working on this one for like 2 hours, so I'm getting excited. Apologies. H2O, good old water. Where would water be? If I was water, where would I be? I don't know. Not here yet. Oh, that's peroxide. Oh, water, let's go. Oh my god, that's high. And water, let's see if it's a gas or a liquid. It is a liquid. Okay, so liquid water, it's negative, I hope I can remember this, negative 285.8. Negative 285.8 kilojoules per mole. I'm going to check back to make sure that I wrote that down right. Okay, I did. Okay, good. And then 2Br2 as a liquid. Going back to Br, seeing if we can find it. Br2. That's a gas. We want it as a liquid. Okay, cool, as a liquid. It's 0. Easy enough, like that. Mole. Alright, cool. So now we're going to be doing this equation over here. So we have H of the reaction is going to be equal to... Alright, so let's start with the products, right? Because that's what the equation calls for. So the first product is water. So I'm going to do 2 times the negative 285.8. I'm not going to add the units just to save myself some space, but just keep in mind that at the end you're going to want your units. And then we're going to add that, because we're taking the sum of the products, to 2 Br2. So Br2 is going to be 2 times 0. That will be fun to work with, minus the sum of the reactants. So the reactants, the first one is 4HBr, so we have 4 times the enthalpy of HBr, which is 36.2. And then we're going to add that to O2, which we have 1 mole of that. It's going to do 1 times 0, easy enough. And I'm going to put this into my calculator. So H reaction is going to be equal to 2 times 285.8. Oops, okay, I literally typed it wrong. That's embarrassing. Alright, so here we have negative 571.6, and I'm gonna just, you know, say we don't need to do that because it's times 0, which is gonna always be 0. And then I'm gonna subtract that from 4 times negative 36.2, which will give us negative 144.8. And then from there, we're going to be doing just our basic math to add those together. So we're going to do negative 571.6 plus, because, you know, when you're subtracting a negative, it becomes a plus, 144.8. And we get negative 426.8. They don't give us sig figs, so I'm just going to put it as that. Professor Sherlock will probably either tell us or give us sig figs to use. But yeah, so that would be our answer, and it'll be in kilojoules per mole. I don't know where I even got this problem, but I'm going to see if I can find it. Oh, okay. Negative 4. Okay, yeah, the answer would be A then. Cool. Alrighty, so there's our answer for that, and that is the end of the video. As always, reach out with any questions, and thank you all for watching.